Today we are talking about the Pythagorean and reciprocal trig identities. Before we get started with the identities, I want to talk a moment, just a little notation, thought, comment. Sine of x all cubed can be written as sine cubed of x. Those mean the same thing. When we put the power in that spot on a trig function, it means that we are raising the entire function to that power. So it means the same thing as sine x times sine x times sine x. If we write the power only on the x, it does not mean that we're raising the entire trig function to that power. It means that only the x is being cubed, only the argument has that cube. So students get that. They get that really easily, the difference between those two things. However, what would be the meaning of sine of x cubed written like this? And I will tell you that it varies. According to the calculator, if we put that into our calculator, if we typed into our calculator, as soon as we put sine, it's going to automatically give us that parentheses, right? If we put just an x in there, close the parentheses, and then put the cube out there, the calculator will think that you are cubing the entire sine function if you do that. For the calculator, that means the same thing as that to the calculator. Of course, the calculator will make you put parentheses around the argument. But these mean the same thing on the calculator. But in most textbooks, if you write, they will write this, and they will mean only the x is being cubed. That's what they will mean. So they say that that is that. So it's very different. So my advice to you is to not use that notation. If you have a power going on in a trig function, use parentheses to clarify which one you mean. Do you mean this or do you mean this? Okay? So avoid using that notation. I say that it's ambiguous. We don't know. We are unsure what that means. Okay? Now, I will tell you this though. I'm so used to seeing this in this form, the way the textbook says it. So if you do write this, I will assume that you mean that. Okay? I'll assume that you mean this. FYI. All right. Before we go on, we need to talk about QED. In some problems, we're going to be asked to prove that one expression is equivalent to another, or show that one expression is equivalent to another. We will do this using what are called identities, and we'll manipulate one side, one expression, to make it be the same as the other one. And we're going to learn several different types of identities, and we already know two different types, the reciprocal and the quotient identities. But once we have shown this, once we have proven this, it is very customary to write QED afterwards. Is it necessary? Will it be wrong if you don't write QED? No, it's not going to be wrong. If you show it, you show it. It's just customary to write this at the end of a proof. Okay? QED comes from that Latin expression, which translates to which was to be demonstrated. Okay? And like I said, we often write it at the conclusion of a proof. Okay? All right, let's get to our reciprocal identities. We already know these. Cosecant x is the same as 1 over sine of x. And if that's true, then sine of x could be written as 1 over cosecant of x, if we wanted to. Secant x is 1 over cosine x, so cosine x is 1 over secant x. Cotangent x is 1 over tangent x, so tangent x is 1 over cotangent x. We've already been using those. We already know that those are all true. The quotient identities we've also used. Sine x is I'm sorry, tangent x is sine x divided by cosine x. Cotangent x is cosine x over sine x. So we've already been using those. Nothing new there. We're just going to be doing some different things with them now. Take a look at some examples. Okay, number 1. The instructions say to prove that tangent x cosine x is equivalent to sine x as long as cosine x is not 0. So, we start by writing what we are beginning with, and we are beginning with this guy right there. So that's where to start. We're going to say that this is equal to something, maybe equal to something else, equal to something else. At the end, it's going to be equal to sine x. Okay? So what can we do with tangent x times cosine x? Well, I can change tangent x to sine x divided by cosine x. And then I'm writing that times cosine x. If you prefer, you can write that over 1 if you like. Well, those reduce out. As long as cosine x is not 0, those cancel out, leaving just a sine x. QED. We're done. I don't mind if you go across or down. I don't mind. Okay? But we are saying that they are equivalent, so if you write it down, I'm going to assume that you have equal signs in each one of those. Okay? More clearly, you should put equals each time. All right. Next one. Let f be this function and g be that function. Let's show that f is equal to g as long as cosine x is not 0. So I'm going to start with f. Okay, and I know what I'm trying to do. I'm trying to make it be that. So that's in the back of my mind. This is what I want it to be. So we can do a couple of different things. I might begin by changing cosecant x. You know what? I might just leave it first. I might just leave that cosecant x times cosine x. But I'm going to write tangent x as 1 over cotangent x. And when I write tangent x as 1 over cotangent x, it brings the cotangent to the top. So this is times cotangent x. Instead of dividing by tangent, we can multiply by cotangent. Means the same thing. Cosecant x is 1 over sine x. Cosine x is cosine x. If you like, you can put it over 1. You don't have to. Cotangent x is cosine x divided by sine x. And this gives us cosine squared x divided by sine squared x, which is cotangent squared x. QED. I am now realizing I really didn't have to change this cotangent. I didn't actually have to change cotangent to cosine over sine because it was already cotangent. I could have just done this and made this cotangent right there. And then I would have had cotangent times cotangent, which is cotangent squared. So with trig functions, there's oftentimes more than one way to do something. Sometimes one way is shorter than another, but it doesn't matter which one you choose, as long as you get there. We arrive at the same place, even if we take a detour or a shortcut. Number 3, f is defined by this function. Which of the following is equivalent, as long as cosine theta is not 0? All right, so f of theta is tangent theta plus secant theta divided by secant theta. Okay. I can see a couple of different things I could do here. It's always the case, almost always the case with trig functions. But one thing that I like to advise students to do, if you're confused, if you don't know what to do with something, change everything to sines and cosines. So in place of tangent, I'm going to put sine theta over cosine theta. That's what tangent is. Plus, in place of secant, I'm putting 1 over cosine theta. In place of secant, I'm putting 1 over cosine theta. Now I see all these little fractions, and every little fraction has a cosine theta as its denominator, so I'm going to get rid of it by multiplying top and bottom by cosine theta. Top and bottom by cosine theta. If I do that, cosine theta times this is just sine theta. Cosine theta times this is just a 1. And on the bottom, I just have 1. So this is true as long as when we cancel out these cosines, that's where the if cosine theta is not 0 comes from. Because you can only cancel those out if it's not 0. Well, you can cancel it out. You can reduce it out regardless, but these are only equal if cosine theta is not 0. So my answer is B. Next up, let h of x be this expression. Which of the following is an equivalent expression for h on the domain of h? Alright, so h is sine x times cosine x times tangent x times cosecant x. I'm going to go ahead and write cosecant x as 1 over sine x times secant x, which is 1 over cosine x, times cotangent x, which is 1 over tangent x, times ln x. Well, here I see a sine x times a 1 over sine x. They reduce out. Here I see a cosine x times a 1 over cosine x. They reduce. Tangent x times 1 over tangent x. They reduce. I'm left with ln x, B. So that is using the quotient identities and the reciprocal identities. Now let's take a look at the Pythagorean identities. Okay, I'm going to start with our old friend, our right triangle that we drew when we first began trig. We drew this right triangle in the first quadrant. Yeah. And here is our, let me get a different color here. Here's our theta. Okay. If this point is xy, that means this length is x, this length is y, and this is the radius of a circle, so I'm going to call it r. Okay. It may be a unit circle, but it may not be, so I'm going to call it r. When we had a unit circle, it was always 1. Okay. Using SOHCAHTOA, I know that sine of theta is y over r, opposite over hypotenuse, which means that y is equal to r times sine theta. Cosine theta is adjacent over hypotenuse, x over r, which means that x is r cosine theta. So we know that those are true. Now let's get the Pythagorean theorem involved. What's the Pythagorean theorem for this triangle? It is x squared plus y squared is equal to r squared. But I know that x is r cosine theta and y is r sine theta. X squared, therefore, would be r cosine theta squared. Y squared would be r sine theta squared, and that must be r squared. Well, r cosine theta all squared is r squared cosine squared theta. R sine theta squared is r squared sine squared theta. I can factor out an r squared from both of these terms, and now I can divide both sides by r squared, which we can do because r is not 0. It's the radius of this circle, so it's not 0. I can divide both sides by r squared, and we get this. This is true for all thetas. We usually see these with, we can use them with a theta, you can use them with an x, you can switch these two. Because it's a sum, you can switch them. sine squared plus cosine squared is equal to 1. And this is the first of our Pythagorean identities. It came from the Pythagorean theorem. It's the first one. Okay. Let's take our first one here. Let's take sine squared plus cosine squared is equal to 1. And let's divide both sides by sine squared. Let's divide both sides by cosine squared first. Dividing both sides by cosine squared of x. If I do that, I have sine squared over cosine squared, which is tangent squared, plus cosine squared over cosine squared, which is 1, is equal to 1 over cosine squared, which is secant squared. The second of our Pythagorean identities, right there. Okay, let's take our main Pythagorean identity, sine squared plus cosine squared x is equal to 1, and this time let's divide both sides by sine squared x. Well, I have sine squared over sine squared, which is 1. Cosine squared over sine squared is cotangent squared. 1 over sine squared is cosecant squared. So this is our second of our trig identities. Not trig identities, Pythagorean. This is the third of our third and last Pythagorean identity. So we have 3 of them, 3 Pythagorean identities, okay? One of them has sine and cosine in it. One has tangent and secant in it. One has cotangent and cosecant in it. Okay? Kids like to remember this one. It's easy to remember, and they remember it well. Sine squared x plus cosine squared x is 1. They like that one. They like it a lot. They remember it. Okay? The other 2, they get muddied, they get muddled and separated, and kids forget about them completely. They tend to, but I know you guys will not, because I'm going to teach you a way to remember them. Okay? Tangent squared x plus 1 is secant squared x. One way to remember that is tan 1s are sexy. Tan 1s are sexy. Tan 1s are sexy. Kids like that one. This one, it's not as memorable, but coat 1s are cozy. Tan 1s are sexy, kids like. Okay? And if you know this one, then you should be able to get to this one, because replace tangent with cotangent, keep your plus 1, replace secant with cosecant. Okay? Another way that I like to have kids remember this is that secant and tangent, they are friends. They're good friends. They like each other a lot, a lot, a lot. They go together. Where you see one, you see another. Okay? You always see them together. Cotangent and cosecant, they're friends too, but again, I remember one, and then you can get to the other one if you want to. This is going to be true all through calculus as well. When we take derivatives and integrals, if you see a tangent, you're going to see a secant. Every time. Okay? If you see a secant, you're going to see a tangent every time. So it's true all through calculus. They're friends, they hang out together. Okay? Now, secant loves tangent. However, secant is a little bit self-centered. Self-centered secant. Secant loves tangent a lot, but secant likes itself better. So secant likes to stand out. So secant is alone on one side of the equal sign. This will also be true in calculus, you guys. So get this straight now, okay? Secant is self-centered. They stand out. Okay, somehow they stand out. Alrighty, let's do some proofs, some problems using this. Okay, Pythagorean identities. Okay, the first one, sine squared x plus cosine squared x is equal to 1. You can replace the x with thetas if you prefer. It doesn't matter. It doesn't matter. It could be an m, an n, a p, a q. I don't care what they are. If they're the same, then sine squared of it plus cosine squared of it is 1. I don't care what's there. It could be anything. All right? Sine squared plus cosine squared is 1. Period. Okay? Next one. Tangent squared plus 1 is secant squared. Same thing with the argument. I don't care what the argument is. That argument can be anything. There could be a cow sitting there. Tangent squared of a cow plus 1 is equal to secant squared of that cow. All right? And then the last one is the one with cotangent. Cotangent squared plus 1 is cosecant squared. Those are the 3 Pythagorean identities. You need to know these. However, you need to also be able to manipulate those. Because if sine squared plus cosine squared is 1, then that means that if we subtract cosine squared on both sides, we'll get 1 minus cosine squared is equal to sine squared. That's not a new identity. That's just a manipulation of our Pythagorean identity. All right? Same thing with this. If you have secant squared minus 1, that's equal to tangent squared. What if you had 1 minus secant squared? That would be negative tangent squared. So be able to manipulate these using your algebra. Okay? All right, number 5. This function is equivalent to which of the following? All right. Well, I see I have 1 minus cosine squared theta over cosine squared theta. Okay, what can we do with that? What can we do with that? I can think of a couple of different ways to do this. The first and most obvious one to me is I see a 1 minus cosine squared. 1 minus cosine squared, if sine squared plus cosine squared is 1, then 1 minus cosine squared is moving this cosine squared to the other side, and that will leave the sine squared by itself. So, if sine squared plus cosine squared is 1, then if we subtract this over, 1 minus cosine squared, that will equal sine squared. So 1 minus cosine squared theta is sine squared theta. And sine squared theta over cosine squared theta is equal to tangent squared theta. Tangent squared theta. Next up, this expression is equivalent to which of the following? Well, I have sine x plus 1 times sine x minus 1. Well, that is equal to, I can FOIL this out, sine squared x minus sine x plus sine x. The middle terms zero out, and then I have the last term is this minus 1. All right, let's go off to the side. Sine squared plus cosine squared is equal to 1. I have sine squared x minus 1. What can I do to get sine squared x minus 1? Well, sine squared x, I'm subtracting 1 on both sides, and I'm moving the cosine squared to the other side where it's going to be negative. So this is equal to negative cosine squared x. Watch your signs on those. It's B. Number 7. On its domain, this expression is equal to what? All right, so we have cosine x plus tangent x times sine x. I'm going to go ahead and change tangent x to sine x over cosine x. Okay, so now I have cosine x plus sine squared x over cosine x. All right, I'm going to get a common denominator. What's the common denominator? The common denominator is cosine x. It's the only denominator. I need to multiply this thing by another cosine x, right? Cosine x over cosine x to get that common denominator. So this is going to be cosine x times cosine x, or cosine squared x, plus the other numerator. And now I have that. But cosine squared x plus sine squared x is 1. So that expression that looked so odd was just another way to write secant x. One more. Here's f, here's g. We're supposed to show that they are equivalent to each other as long as these two conditions are true. All right, so f of x is equal to this. Okay, it's already in sines and cosines, so I'm not going to change it to sines and cosines because it's already there. In class, I'm going to let you guys brainstorm what do you think we can do with this thing, and you'll come up with a variety of things to try, and quite likely somebody will come up with the thing that we can use to get to this. I'm going to multiply top and bottom by the conjugate of this numerator over itself. The conjugate of 1 minus cosine is 1 plus cosine. Whatever you do to the top, you got to do to the bottom. Okay. Up on top, I'm going to FOIL it out. So 1 times 1, the middle term is going to zero out, which is what happens every time when you multiply by a conjugate. The middle term zeroes out. And then we have minus cosine squared x. In the denominator, do not distribute. Leave the sine x by itself. Don't distribute. If you do, you'll just have to factor it in a second, which is fine, but why distribute if you have to turn around and factor back? Okay, 1 minus cosine squared. What is 1 minus cosine squared? Well, sine squared plus cosine squared is 1. I have 1 minus cosine squared, so I'm subtracting cosine squared on both sides, and that is equal to sine squared. So this is sine squared x divided by sine x times 1 plus cosine x. One of the signs reduces out as long as sine x is not 0. So we have sine x divided by 1 plus cosine x. If sine x is not 0, and if cosine x is not -1, what would make that? That would make this undefined. Originally it was not undefined, and now it is. So those two have to be added there. So QED. That's that. So we did the reciprocal identities, the quotient identities, and the Pythagorean identities.